Okay, we're going to do notes today over solving exponential and logarithmic equations. We've got a lot of different examples that you might encounter. So the first one is using the same base rule. If you can get the same base is equal on either side, then you're able to solve this. So on this one, we've got 2 to the x on the left. We can change 512 to be 2 to the 9th power. So now we've got the same base. We can just eliminate that base and set the exponents equal. So that will be your answer. On number 2, probably the easiest way to solve this problem would be to move this log over to the right-hand side. So you'll have the natural log of 5 equals the natural log of x. As long as you've got one log equal to one log, you're able to solve for those arguments. So in this case, this can be canceled out and we can set those arguments equal to each other. So 5 will equal x, and that's your solution. On number 3, we're going to use the same base rule again. I can change 125 to be 5 to the 3rd power, and I would want to do that because this 1/5 is the same thing as 5 to the -1 power, and then you've got that x that's already the exponent for that one. Now that we've got the same base, I can eliminate those bases and set the exponents equal to each other. So -1x equals 3, which makes x equal to -3. On number 4, if your variable is an exponent, you want to convert this to a log, as long as you have that isolated. Okay, so converting this to a log, I would say log of that base e is equal to 13, or I'm sorry, log base e of 13 is equal to x. So then, remember, log base e is the same thing as the natural log of 13, and that equals x. This is an exact answer. If you were asked to give a decimal answer, it would be 2.564. Okay. All right, on number 5, this time our variable is the argument of a log function, so we need to convert it to an exponential function. So remember, natural log is the same thing as log base e. In Algebra 2, they might have had you circle this, do the fishhook thing when you were converting that. So this would become e to the -8. Remember, the log function always equals the exponent, and the log function and the exponent always have the same base, and that equals x, and that would be an exact answer. If you were to give me the decimal, it would be 0.000, oops, that's not right, 0.00335. Okay, on number 6, remember, if you don't have a base written, it's understood to be log base 10. Okay, so we are going to convert this to an exponential function again because x is the argument of that log function. So to do that, that's my base, and I'm going to set it equal to that x. So it'll be 10 raised to the -2 power equals x. Remember, 10 to the -2 is the same thing as 1 over 10 squared. So x equals 1 over 100, or you could have written it as 0.01. Either answer is fine. Okay, on number 7, again, we've already got a situation where we've got the same base. So since we have the same base, we can ignore that and set the exponents equal to each other. And now we have a quadratic to solve. When you have a quadratic, you want everything on the same side and you want it to be equal to 0. So I'm going to move that x squared over by adding it. Now I can factor, and that factors to be x plus 3 times x plus 2. And then setting each factor equal to 0, I get x equals -3 and x equals -2. And those are my solutions, and I need to show both of them. All right, on number 8, our variable that we're looking for is an exponent, so I need to convert it to a log function. But before I do that, I need to isolate this. I need to get rid of that 4. So first thing I'm going to do is divide both sides by 4, and that gives me 3 to the x equals 16. And then I'm going to solve for x by converting it to a log function. So that'll be log base 3 of 16 equals x. And this is an exact answer. If I had asked you for a decimal answer, you would have said 2.523. Okay. Okay, so on this one, we're going to solve on number 9. We need to isolate this. Remember, when you're solving an equation, you take your order of operations, parentheses, exponents, multiply, divide, and add and subtract. And when you solve, you undo those order of operations backwards. So we have to undo any adding and subtracting first. So I need to move the 5 over here by subtracting it. That gives me a negative 3 e to the x equals a negative 3. Now we're going to undo any multiplication and division. So I'm going to undo that multiplication by dividing both sides by negative 3. So divide this by negative 3 and this by negative 3. And what I'm left with is e to the x equals a positive 1. Well, the only way for e to the x to equal a positive 1 is if x equals 0. E to the 0 power, anything to the 0 power is 1. All right, doing the same thing, we're going to isolate this. So I'm going to move the 4 over first. I get 6 times 2 raised to the t plus 5. Oops. And that equals 7 when I subtract 4 from both sides. And then I'm going to divide by 6. So I get 2 to the t plus 5 equals 7, 6. Okay, now I'm trying to solve for this variable. And it's in the exponent field, so I have to convert it to a log function. So doing that, I'm going to say log base 2 of 7 6. I'm going to put that in parentheses. And that'll equal t plus 5. All right, and then I'm still solving for t. That's what I'm needing to solve for. So I've got to move the 5 over. So I'm going to do that by subtracting. So we'll have log base 2 of 7 6 minus that 5. Now it's important that I had parentheses around that 7 6, so you know the minus 5 is not with the log function. And that equals t. And that's an exact answer. If you were to be asked for the decimal answer, it would be a negative 4.777. Okay, on number 11 on the next page, we're solving for x, and x is an exponent, but it's in 2 places. So the easiest way to do this is to factor. And if I ask you to factor something like, I don't know, m squared minus 7m plus 12 equals 0, you would factor that to be m minus 3 times m minus 4 equals 0. Well, you've basically got the same situation here. You've got e to the 2x, and then you've got this e to the x. So think of this as e to the x here and here in your factors, because e to the x times e to the x is e to the 2x. And then you're going to have minus 3 and minus 4. And then you'll set each factor equal to 0 in order to solve. And so solving that, we get e to the x equals 3, or e to the x equals 4. And then convert it to a log function. So that's going to be log base e of 3 equals x, or in other words, the natural log of 3 equals x. Or log base e of 4 equals x, so the natural log of 4 equals x. And both of these are exact solutions that you would use. If I'd ask you for the decimal value, you would have just said 1.386 for this one and 1.098 for this one. Okay, we'll do number 12 the same way. Think of it as like an m squared minus 3m plus 2 equals 0. And that would factor to be m minus 2 times m minus 1. So this will be e to the x minus 2 times e to the x minus 1. Okay, so we are going to set each of those factors equal to 0. And then solving, I move the 2 over, then convert it to a log function. So the natural log of 2 equals x. Here we would do e to the x equals 1, so the natural log of 1 equals x. Well, remember, if you've got natural log of 1, that's one of our identities, so natural log of 1 is just 0, so we're going to put x equals 0 there. And then this is an exact answer. If I ask you for a decimal, it would have been 0.693. Okay, solving logarithmic equations. Again, your x is in the argument of the log function, so we're going to convert it to an exponential. And when we do that, remember that's the same thing as log base e of x equals 2/3. So converting it to an exponential function, it would become e to the 2/3 equals x. And that's an exact answer. The decimal answer would be 1.947. We'll either tell you to give us the exact answer or we'll ask you to round it to a certain value. Usually it'll be 3 decimal places or to the thousands. Okay, on number 14, again, as long as you have one log equal to one log and they have the same base, you can just ignore those and set the arguments equal to each other. So 3x plus 2 equals 6 minus x. And then you're able to solve it from there. So moving the x over here, I'll add it and it becomes 4x. Move the 2 over and it becomes 4. We'll move the 2 over by subtracting. Divide by 4 and I get x equals 1. Now, I don't want to say that's for sure the solution. Whenever you get a value and you're solving for x and x is part of the argument of a log, whatever you're taking the log of cannot be negative. You can't take the log of a negative number. So I need to make sure that when I plug that 1 in for x, that I get a positive value, which I get 5, and that's positive. Or if I plug in 1 over here, I get a positive 5. So as long as I'm taking the log of a positive value, that's okay. So that answer works for me. All right, number 15. Again, you need one log equal to one log in order to solve this. So I'm going to have to combine these using my rule of logs. And because we're subtracting, we can combine those by dividing the arguments. So the log of base 3 of 5x plus 13 over 6 equals the log base 3 of 3x. Okay, now I have one log equal to one log, so I can ignore the log part and set the arguments equal to each other. So 5x plus 13 over 6 equals 3x. All right, I'm going to solve this by multiplying both sides by 6 first. This will cancel with this, and I'm left with 5x plus 13 equals 18x. I'm going to move the 5x over by subtracting it, so that'll give me 13 equals 13x, and then I'm going to divide by 13, so I get x equals 1. And that's my solution. Again, I need to plug it back in. If I plug in 1 into this argument, I'm going to get a positive value. This is just 6, so I don't have to worry about it there. And then if I plug in 1 right here, I'm getting a positive value for the argument as well, so that 1 will work. All right, number 16, we need to isolate this. So the first thing I'm going to do is move the 6 over by subtracting it. So that gives me 3 natural log of x equals a negative 2. Divide both sides by 3, so I get the natural log of x equals a negative 2/3. Remember, that's the same thing as log base e of x equals a negative 2/3. So since the variable that I'm solving for is an argument, I have to convert it to an exponential function. So this will become e to the negative 2/3 equals x. And that's my exact answer. If you did e to the negative 2/3, remember that negative 2/3, that's the same thing as saying 1 over e to the 2/3. It'll be a positive value, so it'll work when you plug that in. The decimal value for that is 0.513. Okay, let's do another one. Okay, on number 17, we're going to divide, we need to solve for x, and we need to isolate this. So I need to divide both sides by 3. So that gives me log base 4 of 6x equals 3. Now then, I'm trying to get this x by itself, so I'm going to convert this to an exponential function. So 4 to the third power will equal 6x. 4 to the third power is 64. Divide both sides by 6. So you're going to divide this by 6 and divide by this by 6. And you'll end up with x equals 64/6, which is the same thing as x equals 32/3. And that's your answer. And it's a positive 32/3, so when you plug it in back into the argument up here, you'll get a positive value. So you can take the log of a positive value. Okay, number 18, I need to combine these to be one log. And so because of this adding right here, you can combine those arguments by multiplying them. So log base 10 of x times x minus 9 equals 1. Now that I've got one log equal to a number, I can convert to an exponential function. So that becomes 10 to the first power equals x times x minus 9. And then solving that, I'll get 10 equals, distribute your x, and you get x squared minus 9x. Because I have a quadratic, I have to have it equal to 0 so I can solve it. And then we're going to factor that. So we'll factor that to be x minus 10 times x plus 1, and then set each factor equal to 0. So x minus 10 equals 0, which means x equals 10, or x plus 1 equals 0, which means x equals negative 1. Now remember, when you go back to your original problem, this, for example, log base 10 of x, I'm going to be plugging in this negative 1 right here, and I can't do the log of a negative number. So we are going to ignore that answer choice, and this will be our only answer for this problem. When I plug in the 10, I get positive values that I'm taking the log of. Okay, one more problem. On number 19, we're going to combine these to be one log. And when you combine them, because of this plus, we'll multiply them. So it'll be log, and that's understood to be a base 10, even though it's not written. And then that's going to be 5x times x minus 1 equals 2. Now I'm going to convert it to a log function, or I'm sorry, to an exponential function. So that becomes 10 squared equals 5x times x minus 1. Okay, simplifying this, I get 100 equals 5x squared minus 5x. Move everything over to the same side so it's equal to 0, and I can factor. Okay, I'm going to divide everything by 5 just to make this easier. As long as you have an equal sign, you're allowed to divide through by a number, as long as you divide every single term by that number. So that gives me 0. When I divide 0 by 5, it's 0, and then equals x squared minus x minus 20. Then factoring that, I get 0 equals x minus 5 times x plus 4. That's how that would factor. So my solutions are x equals 5 or x equals negative 4. Remember, when you plug those back in, like if I plug in that negative 4 here, I'll be taking the log of a negative 20, which is not possible. So that answer cannot be used, and this is our only solution for that one. All right, let's do some more. Okay, on number 20, we've got some word problems here. You have deposited $1,000 in an account, so that's your principal. That's what you're going to be depositing. And this is it's into an account that pays 6.25% interest, so we would write that as 0.0625. And that's our rate. It's compounded continuously. When you see that, you should be thinking, to get the amount, I'm taking my principal and I'm using the PERT equation. So we're going to be using that equation. How long will it take? So I'm looking for the time. How long will it take for my money to double? Well, if I started with 1,000, double would be 2,000. So that's my A value. So when I use my equation, my PERT equation, my A value is 2,000. That's when it's doubled. I originally started with 1,000. And then E, my rate was 0.0625. And I'm looking for time. Okay, so we are going to try to isolate this. So that means the first thing we want to do is divide both sides by 1,000. So that gives me 2 equals e to the 0.0625t. Now we're solving for t, and t is an exponent, so that means I need to convert it to a log function. So in doing that, that's going to be log of the same base, e, of 2 equals that exponent, 0.0625t. We're solving for the t, so we're going to divide both sides by 0.0625. So t equals, an exact answer would be log, which actually, let me rewrite that. And log base c is the same thing as the natural log. So the natural log of 2 over 0.0625. That's an exact answer, but we're talking about time, and I'm pretty sure you wouldn't want to tell somebody that's how long it's going to take them. So we would get a decimal value, which would be 11.090 years. Remember, these equations are always used, we use years for these equations. Okay, number 21. Okay, 21, the number y of endangered animal species on a protected wildlife preserve from 1990 to 2004 can be modeled by this equation. And we're doing it from time, goes from 10 to 24. Where t represents the years, t equals 10 is 1990. And then t equals the 24, that's 2004. Okay, so it's during which year did the number of endangered species reach 342? So we're using this equation that they gave us, y equals a negative 117 plus 159 natural log of t. And this 342 right here, that's going to be our y value that we're going to plug in. So 342 equals 117 plus 159 natural log of t. All right, so we're going to solve this by undoing our order of operations backwards. We'll undo any adding and subtracting first, so we'll add 117 to both sides. And when we do that, we get 459 equals, that cancels, 159 natural log of t. Now I'm still trying to solve for t, so we need to isolate this, so we're going to divide both sides by 159. Alright, in doing that, I'm going to leave this as a fraction, 159, or 459 over 159, because it doesn't come out nice, equals, those cancel, the natural log of t. Now we're trying to solve for t. T is the argument in a log function, so we need to convert that to an exponential function. Remember that log, that's the same thing as log base e of t. So when we convert it, it'll be e raised to the 459 over 159 equals t. All right, that's an exact answer. If we get the decimal value, we would get t equals 17.935. So if at time 0, if at time, when time was 10 years is 1990, time of 0 would be 1980. So I'm going to be adding that 17 years to 1980, which would be 1997. So it's closer to the end of 1997. I'm just going to say during 1997. You could say towards the end if you wanted to, because of that 0.935. But that would be the answer for that one. All right, thanks guys.